Okay, hello. Okay, it's good. I think it's like 3:31, so I think we can go ahead and get started. Yeah. So I'm really excited. Today we have Professor Ann Sickles. Ann is a professor of physics from University of Illinois, Urbana-Champaign. She got her PhD from Stony Brook University, where she was part of the sPHENIX collaboration at RHIC. She was in a postdoc and then a staff scientist at Brookhaven National Lab before she went to University of Illinois in 2014. Ann and her group are members of both the ATLAS collaboration at the LHC and the sPHENIX collaboration at RHIC. Ann has held various roles within the collaborations, including she was the Heavy Ion Working Group convener for ATLAS, and she's currently the chair of the publication board for sPHENIX. And more recently, she was one of the conveners for the QCD town hall for the nuclear physics long-range plan in 2022. And today, Ann will tell us about nature's hottest fluids, measuring the inner workings of the Quark Gluon Plasma. So welcome, Ann.
Thank you. Thanks for that nice introduction, Laura. And does this work, or do I have to putz with the microphone? Is this okay? That wasn't me, right? Okay, great. I saw a thumbs up from the back, so I'm going to assume it's fine. Okay, we're going to do this. Okay, so I'm going to tell you about the Quark Gluon Plasma, and I mean, obviously there's a lot of people here in this room and in this department that are also experts on this. And so, as Laura mentioned, I'm part of ATLAS and sPHENIX. The people here are part of ELISE and STAR. And so I think that a lot of, we have our own perspective, but there's a lot of agreement in general overall. So I'm going to tell you about my take on it. But certainly a lot of people here are also experts in this. All right. So with that, so I said that this is nature's hottest fluid. So the first question is, well, how hot is that, right? It's certainly hotter than today. It's certainly hotter than Wyoming, where I was last week. So a nice day is about 25 degrees Celsius or 80 degrees Fahrenheit. It seems outrageously warm coming in February and very light, very nice. So lava is pretty hot, right? You should definitely not put your fingers in it. It's not going to go well. So that's about 2,000 degrees Fahrenheit. The center of the sun, we're talking like 27 million. So okay, that's pretty hot. It's a giant fusion reactor. That's kind of what you expect. Supernovas, if you look out into the sky, ring at about 180 billion Fahrenheit. So that's the hottest thing that exists naturally in the world for the universe, as far as I understand it. So the Quark Gluon Plasma is what I'm interested in, and that is more than 3 trillion degrees Celsius. So this is really freaking hot, okay? And I don't have a nice picture that I can pull from Wikipedia for that. And so what I'm going to do is I'm going to try to tell you about how we go about trying to construct that picture. So to do that, I have to start off with a little bit of QCD. And so I understand there's graduate students here which are not experts in the strong nuclear force, and that's totally great. So I'm going to talk to you about the proton. And the proton is responsible for basically all the mass of everything that we see around us. For my purposes, I don't care about the difference between the proton and the neutron, which is totally fine, right? So these are some nice pictures, and this is the proton. And maybe if you have some glancing familiarity with it, you know that basically there's 3 quarks. They carry the quantum numbers of the proton. And if you read Wikipedia, that will tell you that there's 2 up quarks and a down quark. And the up quarks have plus 2/3 charge, and the down quark has minus 1/3 charge. And the only way anyone ever remembers that is because they have to add up to 1 to give you up, up, down, which is the charge of the proton. Okay, so these are our 3 quarks. They carry color charge, which is what the way the strong nuclear force interacts. So it's whimsically red, green, and blue. Of course, it's not really like that at all because these are all quantum fields, but that's fine. So this is a kind of a classical picture of the protons. But of course, the proton's a quantum system. So when you look more closely, still in a cartoon version, what you get are these 2 up quarks and a down quark, which were there in the previous one. And I do have a pointer, so I can use that. you get a lot more detail. So there's a few things that pop out here. First of all, these little spring-like structures, those are gluons. Gluons are the force carriers of the strong force. And so these keep the quarks bound inside the proton. And also you can have there's these pairs of quark-antiquark pairs. So these pop in and out of the vacuum. They're called the C quarks. C is an SEA. So this is a virtual sea of quark-antiquark pairs that carry a large fraction of the proton's momentum. And all of this is really wrapped up because the strong force has a very short distance scale associated with it. That's why most of the people throughout most of human history have gone their entire lives without even knowing this force exists, right? All of these details are just wrapped up in the proton, which is wrapped up in the nucleus, which generally, if you don't touch it, doesn't bother you. So that is the property of the strong force called confinement. QCD, you'll see this around, is quantum chromodynamics. This is the quantum theory of the strong force. And quarks, they carry electric and color charge, as I alluded to before, and gluons can carry color charge. And I don't know if I have what makes the strong force different than QED, which is the quantum theory of electrodynamics, is two things. So first of all, the gluons carry color charge. Photons do not carry electric charge, but the gluons carrying color charge means they interact as well. And so you can have diagrams I don't have pictures of here where two gluons merge into a single gluon. You could have a gluon splitting into two gluons. And so these really change the nature of QCD. The other thing that is characteristic of QCD is that the force is very strong. And so this makes calculations very difficult. In very high momentum, you can have weak coupling. This is asymptotic freedom. And perturbative techniques work well. In other regimes, if you try to write down a perturbation series, you end up with a series where each one of the terms gets successively larger. And so analytic calculations are difficult. And by difficult, I mean generally impossible. You can do some of this on the lattice. It's really just generally a pain. Okay, so this is great as an experimentalist, because if I'm interested in QCD, like, this is great. I can work on this experimentally and have a great time. So I'm interested in studying the high temperature behavior of a system that looks like this in a low temperature bound state. So how am I going to do this? I've already said that this is really freaking hot. So what am I going to do to make it such that I can make something so hot? I can't, get out there's a torch over here from some other lecture. I can't get that out and like heat up the nucleus. What am I going to do? Well, I am going to take a big nucleus. This is a nucleus, protons in blue, neutrons in red, or vice versa, it doesn't matter. It's just a bunch of circles. And I'm going to try to heat this up by adding a lot of energy. I'm going to call this the Quark Gluon Plasma. Okay, so how am I going to do that? I'm going to get two nuclei, and I'm going to get them going basically the speed of light, just to share under it. And I'm going to run them into each other. And that the goal is to create something that is the several trillion degrees Celsius that I mentioned. And in order to do this, I can't do this here. I have to do this at colliders. And there's two colliders where this is currently done. So one is the Large Hadron Collider at CERN, and the other is the Relativistic Heavy Ion Collider at Brookhaven National Lab on Long Island. So the CERN program, as people here well know, much of the CERN program at the LHC is to collide protons together, understand QCD in a low temperature sense, and to search for physics beyond the standard model. But 1 month a year or so, they run nuclei together. So the top energy, actually this is out of date, for lead is about 5.02 TeV, so it's 5.3 now. With the advent of the run 3 at the LHC, it's a little bit higher. But so the red line, the LHC is underground. So they can collide nuclei together at 5 TeV. So that's 5 trillion electron volts as the top center of mass collision energy at the LHC. The Relativistic Heavy Ion Collider, it's a smaller scale operation. So this is about 2.5 miles around. It's about at ground level. The accelerator is actually covered by a berm of dirt. You can see the road and the structures around it here in the trees out at Brookhaven. This is a smaller collider that has a smaller collision energy. So the top collision energy here is about 0.2 TeV. So it's 200 GeV, so 200 billion electron volts for the center of mass energy. And so what you see here is that these two colliders have a factor of about 25 difference in collision energy. And so I'll come back to this later. Okay, so I'm going to take two nuclei, get them going really fast, and smash them into each other. So these are two individual nuclei. The accelerator complex has stripped off all the electrons and basically got them going very fast. So they come in. This is sort of a series of pictures. So the nuclei come in and they're Lorentz contracted. So they're basically like pancakes because they're going 99.999% of the speed of light. Some very intense stuff happens. That's what's illustrated here as they collide. And then you make this. This is an illustration, a schematic illustration for the Quark Gluon Plasma. This is what I'm interested in. Then what happens is, of course, it cools off. It expands into the vacuum that is the beam pipes at the LHC or at RHIC. And then you get a bunch of hadrons. So these are the stuff of particle physics: pions, kaons, protons, lambdas, all sorts of things like that. And you can measure much of their momentum, their energy. Sometimes you measure their mass, often through techniques like time of flight. So this is what I, as an experimentalist, have access to. So here's what my collider friends give me. Here's what I have access to. And here is what I'm interested in. So that all takes place in something of the order of 10 to the minus 22 seconds. So that's how long this entire process happens. And so what you learn from this is that you can't watch this happen in real time. You can't take a video of it. You can't even interact with it. You can't say, here's a collision and I'm going to do something to it and watch what it does. All you can do is just measure the stuff that comes out. And so again, like one of the reasons I got into this field, because I feel it's very experimentally driven. And this seems like a problem that you're missing a few too many constraints on. And I'm going to try to show you that that's not the case. But obviously, this is kind of a puzzle where you're missing the box, perhaps. And so to do that, you need big particle detectors. So you're trying to measure something that's very, very small. And so, of course, you need giant, expensive detectors. So this is the LHC, or Atlas at the LHC. This is one of the experiments that I work on. This is a scale of about 25 meters. It's about 45 meters over this way. This sits underground at the LHC. So one beam would come in this way. The other one would come in from that side, and they would hit each other in the center of the detector here, which I cannot keep my pointer focused on. And then the detectors come out like an onion, right? So there's very precise silicon detectors near the interaction point. There's calorimeters further out. And finally, there's muon detectors. Even further out, and not shown here, there's far forward detectors as well that help us characterize the collisions. And so Elise, sPHENIX, STAR, many of them have the same general concept, right? And so this is just a picture of one that I work on. And so what do we see? This is a single lead-lead collision in Atlas. And each one of these lines here is a charged particle that has come out of one single collision. And so a lead-lead collision, because lead are so big compared to protons, 208 nucleons, protons and neutrons in lead, compared to one in proton. It's like up to about 1,000 proton-proton collisions. It's sort of the equivalent of a lead-lead collision. And we can make up to about 10 to the 4 particles in a single event. So we have a lot of information about these collisions. It's an incredibly complex system. And Atlas, was designed to look for physics beyond the standard model and measure the Higgs. And it turns out that the granularity and resolution that is appropriate for that is actually great for a heavy ion detector as well. So we can run the Atlas tracking. Many of these are charged pions. Some of them are kaons, things like that. We don't actually have access to the types of particles they are because we don't measure the time or the mass. Elise can do things like that, but Atlas cannot. But so each one of these is a particle. And so we're going to look at the correlations between these particles. We're going to look at the energy that's recorded in the calorimeters, which is alluded to here by some of these histograms. And we're going to try to figure out what we can learn about the matter that's created in the center of these collisions. Okay, that's what we're going to try to do. Now I'm going to tell you about geometry on an extraordinarily small scale. And studying the heavy ion collisions in the quark gluon plasma actually turns out to be a very small scale geometry lesson. So for us, the nucleus is very small. But for the nucleus, it's not small. If a lead nucleus is made up of 208 protons and neutrons, then actually there's variation that can happen on those scales. So these are simulations of 3 different collisions between lead nuclei that I ran on my laptop. And so let's walk through this. So these are in the XY plane. So if we take a collider that is bringing things in from the left and the right along the z-axis, the XY plane is the one that's perpendicular to that. So the nuclei are coming in from both sides. And so in this way, it would be, in and out of the screen. And there's blue circles and there's red circles. So each one of these circles is a proton or a neutron. And the ones that are blue shaded are from the one that's coming out of the screen, and red shaded is coming into the screen, okay? And the ones that are dark, filled in, those are the ones that hit something from the other nucleus. The ones that are just lightly shaded that are on the outside, those are called spectators. They don't participate in the collision. They just keep on going forward. Everything is happening at basically the speed of light. So, something out over here, it's not causally connected to what's happening over there. It's just basically sheared off and goes forward as a nuclear fragment. Okay, so the dark colored red and blue circles are what's available to actually create a quark gluon plasma. That's the energy that's there, that's stopped, that we can measure. And so what you can see is that you get different shapes of this depending on the distance between the centers of these 2 nuclei that hit each other. And this is not something that's controllable by the LHC accelerator people. This is just something that, there's a distribution of this that's just given by geometry. They hit each other at whatever the distance apart they hit each other. So this one here, the impact parameter is very reasonably large. And you get something that's shaped like an American football. Here, the impact parameter is very small, as you get something that's basically round. This one's kind of funny in that it's basically round, but it has weird little islands sticking off the edge. And this is because 208 is not infinity, right? The distributions of the nucleus, the nucleons inside the nucleus is basically described by a Wood-Saxon model, as maybe you learned in a nuclear physics class. But then you're populating it with individual protons and neutrons. And so there's some randomness to this. So there's 2 things that you should probably take away from this. One is the randomness that gives you these fluctuations in the geometry. And one is that there's an overall scale of the geometry that has to do with the impact parameter. Okay, so I'm going to talk about the consequences of this. And this is one of the very early Atlas papers. Elise has similar results. This was one of the most striking things when the LHC turned on. Basically, if you smack a coordinate system on one of these collisions, and you just start counting particles that come out of the collision, right? This is the simplest thing you can do. We're not counting on the particle's momentum. We're not asking for very specific kinds of particles. We're just putting a coordinate system on, and we're asking for the numbers of particles. This is what you get. This is actual data. It doesn't look like data because the error bars are so tiny. And it's beautifully a cosine. When do you ever see something that looks this nice, right? So this is 0 degrees in this angle phi right here. Pi, at pi minus pi and 0, there's about 25% more particles than at pi over 2, or than the average. At minus pi over 2 and pi over 2, there's a deficit of the same amount. So this is just a relative normalization. It's been normalized to have the same area. This is great. And so you see this huge, visible to the eye, modulation in the number of particles. And you can describe this by a cosine. And the amplitude of this cosine is what we call V2. And if you hang around heavy ion physicists for more than about 5 minutes, they start talking about V2. It's impossible to get them to shut up because it's very stark. It's right there. And so what this is telling us that actually the particles know about the geometry. So more particles are coming out the long side of this geometry than out the short side, right? So this is, if we take our American football shaped thing, we got more particles in the purple region spin out the pink region, the top and the bottom. And this actually has profound physics consequences. So I'm going to tell you about that. So we've got our little shape here now. It's a red outline with a few black dots. So if we just think about an ideal gas, right? So the density is very low. If I take, if I take this one, almost no matter which way it goes, it's not going to hit anything, right? It doesn't matter. It goes this way, that way, whatever. There's very little phase space for it to interact with some other particle in this. And that's what an ideal gas is, right? The interactions are not super important. However, if I start to like add more particles in this shape, now all of a sudden, this I do have an animation for. If I look at this one here, the pink one, well, there is a lot of phase space for it to interact with other particles, right? If it goes that way, it doesn't interact. But if it goes almost any other direction, it does interact. So it can understand the geometry. And what the quark gluon plasma is sort of, the way to understand the geometry of where you are in the system is when the density is high enough that the interactions become important. So the quark gluon plasma is the limit of lots of interactions. And so if we, many of us were at a conference in Wyoming last week where there were steep mountains. And so this is basically, this is going down the bunny slope, right? Because the pressure gradient is a lot smaller. And this one here is going down the black diamond, right? A huge pressure gradient. I would be way over here. I'm from Illinois. And so like, for God's sake, stay away from the mountains. So this is the steep pressure change. This is the gradual pressure change. And so if you have these pressure gradients, what happens? This thing will explode out in what I've drawn here is the X direction here. So that is what's going on. You're in the limit of lots and lots of interactions. That's the only way to really describe what's going on, what we see when we start counting the particles. Okay, so the limit of lots of interactions is a liquid. So this is how we get to nature's hottest liquid. So if we were to just characterize this, one thing that you can do to characterize a liquid is you can look at its viscosity. So this is a nice beach. Water is a very low viscosity liquid. The theory of all these liquids is, of course, hydrodynamics, because water is the prototypical liquid. Honey is a very high viscosity liquid here. And so, obviously, that's very different than water. And so the QGP, the quark gluon plasma, is actually an extraordinarily good liquid. And so this is from a Nature physics paper that came out several years ago. And this is the magnitude of this modulation, the V2. This is it measured actually in Elise as a function of centrality, which I'm not going to explain, but it's related to this impact parameter here. And basically what you can do is this is a Bayesian analysis. So you use models of relativistic viscous hydrodynamics, and you change the viscosity in these models, and you ask what kind of V2 you would get, and then you change it until you match the experimental data. And this is the viscosity to entropy density ratio as a function of the temperature. And this is water, helium, and down here is the viscosity to entropy density for the quark gluon plasma that they extract. So it's actually an extraordinarily good liquid. And so this is really the defining feature of the quark gluon plasma. And what the question I would like to answer is why? Why does a strong force at high temperature behave like a liquid? You can look up the QCD Lagrangian, but that's not going to tell you just by staring at it. At least it doesn't tell me why there should be this emergent phenomena at QCD at very high temperature. And so this is the question that I want to answer experimentally. And so to answer that, you need a microscope. I've told you a lot about the bulk properties of the QGP, how it behaves on like large length scales. But in order to understand how that relates to what we know about the strong force, we actually need a microscope to look at very short distance scale interactions between the quarks and gluons. And so that's essentially what we're trying to do here. So what would you like to do? What you'd like to do is you'd like to take a static quark gluon plasma, you'd like to put it in a box, and you'd like to do a scattering experiment. I mean, that's what physicists like to do. You'd like to get a beam of monoenergetic quarks, And then you would like to shoot this static quark gluon plasma and measure everything that comes out the other side. And nature says, no way. So we have to be a little bit more clever. And so what we do is we take into account that the proton, for our purposes, is basically just a bunch of quarks and gluons. So you got two protons here, they're coming at each other. And as I showed you before, they have a bunch of quarks and gluons inside of them. And every now and then a quark or gluon from one will hit and have a hard scattering, a large momentum transfer with a quark or gluon from the other one. And so when that happens, there's a large momentum transfer leads to a large angle scattering. And so that's what you get the red lines here. What happens then is as some confinement kicks in. Nature says, what do you mean? You've got a quark and it's got no friends around it. It's not confined. And what happens is a process called hadronization. To make what I've shown schematically here as all these black arrows, these are just a bunch of hadrons. Pions, kaons, protons, things that are made up of bound quarks, bound states of quarks and antiquarks. And so this is what we call jets. So this is a high momentum phenomena that occurs abundantly, both at RHIC and the LHC. And this is the probe that we're going to use to study the quark gluon plasma. Just to prove to you that this happens, this is actually a several years old event display from Atlas. This is a proton-proton collision. So you can see let's start over here at this one at the top. So this has one beam of protons coming out, one coming in. And the yellow and green are, those histograms are proportional to the amount of energy that is deposited in the Atlas calorimeters. So what you can see is that there's a lot of energy coming out this way, a lot of energy coming out this way. That tells you these jets are back to back. It has to be because momentum conservation. And then here is a more dramatic rendering of the same collision, right? So one beam coming in like this, one beam coming in like this, one jet coming at you like this, and one jet going away from you like this. So this is proof that this happens abundantly at the LHC. And as I mentioned, you can use perturbative techniques. So this is the cross-section for jets as a function of the momentum transverse to the beam axis as measured in Atlas. And all the data points are shown in black. And you can't see the systematic uncertainties, but they're there. The yellow shows you a perturbative QCD calculation. And over here is the theory to data ratio. And what you can see is there's beautiful agreement over, I don't know, about 15 orders of magnitude. 9 is what I said, but I think it's a little bit more. So there's beautiful agreement. And this is not unique to Atlas. All the LHC collaborations have measured this, that we understand this process very well. So this is fantastic. So we have a probe, and we understand it. So this is a great place to start. And so what I want to do is I want to take apart how we're going to use this in a heavy ion collision. So I showed you this event display here, and event displays are great for illustration, and they're not really physics. So what we've done in proton-proton collisions here, so no QGP, is we've just plotted the momentum of the second leading jet compared to the momentum of the highest energy jet in a collision. So this is in proton-proton collisions shown in these stupid orange points. I just don't like the color scheme. My postdoc and I had differences of opinion about this. So that's what you can see. If nature was very simple, these would always be balanced back to back. And so this ratio would always be 1. You can see 1 is the most probable value, or between 0.9 and 1. But it's certainly not the entire distribution. And that's because QCD is complicated. All these gluons, they just want to keep interacting. So you can get events where there's not just 2 jets, but 3 jets or 4 jets. You can get all sorts of things going on. And so that's what gives you this tail of this distribution. But what we've shown here is a model called Pythia, which is a Monte Carlo generator of proton-proton collisions. And you can see it does a very good job describing what we see. So this is good, right? This helps us understand our baseline. All right. So what are we going to do with this? We're going to take these jets that are made in proton-proton collisions, And we're going to remember that protons and neutrons are part of a lead nucleus. And so this happens all the time as we bring these two big nuclei together. And so these things, these jets are created as we make the quark gluon plasma that I was telling you about before. It's inherent in the process. So this helps us get rid of all of our problems about the timescales being too short. The collision itself is making the probe. So we want to look at these back-to-back jets. And this is actually one of the first results to come out of the LHC Heavy Ion program in 2010, I believe. This is an event display, again, from Atlas. And again, we have one beam coming out of the board and one coming in. And again, these bars here are proportional to the energy. And so what you can see is a cluster that is one jet over here. But instead of seeing a balancing jet on the away side, we actually just see a broad, diffuse amount of energy, right? There's no peak right over here. So qualitatively, I would have a picture that this is a jet created perhaps here. If this is the circle is my quark gluon plasma, maybe a jet is created here. And this jet that's going up, it sees a very small amount of the quark gluon plasma. It lives a relatively easy life. It emerges from the plasma relatively unmodified. But its partner has a long path through the quark gluon plasma. It interacts a lot with this very hot medium. And it loses energy. There's stronger interactions. There's lots of interactions, and it emerges much more modified, apparently, in a broader shape. And so this is what we want to try to do. We want to take what we think about the geometry and measure what happens to the jets as they probe the plasma. If they didn't interact, they would be a terrible probe, right? Like, it would be totally useless. But since they do interact, as we saw very early on, this is a way to get at what's going on and to understand the inner workings of the quark gluon plasma. So this is, we can just measure basically the cross-section of jets in these lead-lead collisions. This is a nice measurement from Atlas. And heavy ion people, once they're done talking about V2, they start talking about some ratio they're taking. That's the only thing we do. We take a lot of ratios. So here is RAA. So you can think of it as the number of jets that I see compared to what I expect. So what do I expect based on nuclear geometry and proton-proton collisions? And here's the big QGPs. This is the ones with very small impact parameter. That's in pink. And you can see I'm getting maybe 60% of the jets that I expect. This is as a function of the jet momentum here. If I go to these very peripheral collisions with a smaller QGP, I'm missing maybe 10, 20% of my jets. But I want to talk mainly about these big QGPs where I'm missing a lot of my jets. So basically half of them are gone. This is a phenomenon called jet quenching. And as you can see, if I'm talking about factor of 2 effects, this is not subtle, right? We don't have to we want to measure it quantitatively, but it's not something that we have to convince ourselves is there. It's a big phenomenon. We want to study it. So what I want to do is I want to go back to looking at the dijets, because the momentum conservation that I know is there in proton-proton collisions must be there when these jets are created in the quark gluon plasma. And then I'm starting to lose it. So I want to understand how this momentum balance of jets is modified. So in these orange points are the same points I showed you before. That's proton-proton collisions. And you can see the most probable value is around 0.1 or around 1. This is what my baseline is. Then as I go to the bigger and bigger quark gluon plasmas, and the biggest one here is in black. I apologize for the mix-up of the color schemes, but that's here. And so what you can see, this is that same momentum balance of the jet, the momentum of jet 2 divided by the momentum of jet 1, is that for these jets that are pretty imbalanced, there's not a huge modification. But for these balanced jets, there's about a factor of 3 depletion in the rate of balanced jets going from PP collisions to central lead-lead collisions. So the increasing size of the QGP decreases the rate of balanced jets. Okay, so this is interesting. And these other colors going from red all the way up to purple are looking at smaller and smaller versions of the quark gluon plasma. So what I was curious about, what I'm thinking about, is how to tie this to geometry. Because it seems really that like these jets somehow know that they should be suppressed a lot more than these jets over here. And actually, the jets can be created anywhere in the quark gluon plasma. There's some probability distribution associated with it. I don't know where they're created. I only know the momentum that we measured them at, right? That's all I have access to. So this picture I was telling you about before with a surface bias jet, right? One jet that barely interacts and one jet that goes through a lot. I suspect that these are the ones that are over here with the small modifications, that these, you really have this biased, this jet that's really gone through a lot of the plasma. Whereas here, where I have both jets losing a lot of energy, I think that must be the way to go from this very peak distribution in proton-proton collisions to this really flat distribution that preferentially suppresses these balanced jets, right? So both jets have lost a lot of energy. Actually, the jet cross-section falls steeply as you increase energy. And so you just don't see them because both of them have lost so much energy. So this is a very experimental picture. I'm an experimentalist. I like experimental pictures. So what is actually happening to the jets? I promised you trying to understand nature's hottest fluid, and I've shown you a lot of ratios. So what happens is confinement kicks in schematically, and this is a nice picture from one of my colleagues at Brookhaven. In proton-proton collisions is what you have a quark. Quarks are represented by arrows. The squiggles are gluons. And so all of this is a probabilistic process. This is a cartoon, right? So you have a quark from a jet coming in, and then it starts to interact, right? So maybe it sheds a gluon. Maybe it sheds a gluon over here. Maybe that gluon turns into a quark anti-quark pair. Maybe that sheds another gluon. Maybe it goes along a little bit in time. This is time along the horizontal here. Sheds another gluon, and that gluon splits. So this probabilistic process is called hadronization. At a certain point, all of this should get to a low enough scale that it starts to make things that I call pions, kaons, and protons. But so this is what happens. So once I add a QGP to this mix, well, the shower still develops. However, now there's these additional hooks, which are drawn here in red. And these are the interactions between the developing shower and the quark gluon plasma itself. So this is what the modification is. This is what we want to try to understand, because this is what's going to tell us about the short distance scale behavior. So, in the end, we still have access to the particles, but this branching and showering process called fragmentation has been modified because it's hooked into the QGP. So what I want to do is I want to try to understand that. So there's two ways that I'm going to talk about relatively briefly. One is to vary the structure of the shower, right? This is a probabilistic process, just a cartoon, but obviously there's different ways the shower can develop. So one of those ways is it could start with a quark. We could easily swap out a gluon from here, and that would make a profound difference. But also, just because of the fluctuations inherent in this process, you can have these showers develop in many different ways. Another way is to vary the length the jet travels through the QGP, right? I talked about the lengths, but you can vary the geometry of the system. I'm going to talk about this briefly. One of the things I'm going to talk about is jet substructure. So I've talked about jets as composite objects. I've shown histograms of their energy, but at the bottom, they're just made up of particles. They're particles that are clustered together. They're particles that carry the momentum and energy associated with some hard scattered proton and some quark or gluon. They're a bunch of particles. So here's the particles represented as green dots. But of course, I can look for clustered energy here. And many people in this room are more expert than me in substructure, but we're going to essentially just look for clustered energy. So there's a process called grooming, which aims to look for the structure of the shower that forms the jet. So we drop some of these soft wide angle things that gray them out. But then we see this like nice structure of the jet, right? Maybe there's two little clusters inside the jet. And we're going to measure the distance between that. We're going to call these RG. This is some angle that's characteristic of the jet fragmentation. And so Atlas has measured this in proton-proton collisions. There's very similar work that's been done by Elise. I'm going to show the Atlas stuff here. But this is this RG distribution. We can see it's peaked somewhere around 0.1, 0.01, 0.02. This is in proton-proton collision compared to a bunch of generators. Okay. So we're going to ask, what's the interaction between these missing jets, the jets that have lost energy, and this RG, this characteristic opening angle? So this is the same plot I showed you before, only now we're going to look at the same quantity, RAA, not as a function of momentum, but as a function of RG. We're only going to do it for these most central collisions here, the largest QGP, the pink ones. We're going to look at it as a function of this RG variable. And what's shocking to me is that this really just seems to line up. The RAA seems to be controlled for a variety of momentum ranges, which are shown here in these different colors. The RAA really lines up according to this RAA. And so what I think this tells us is that the way that the jets are quenched is correlated with their opening angle. And that makes sense, right? If you have a very small opening angle, so right over on this left side of the plot here, maybe you just essentially make it through the QGP because you barely interact with it, right? And there's a very small suppression, maybe 20%. Whereas if you're some fat jet with a very large opening angle, you interact with the QGP a lot. You essentially, you're very caught up in it. I'm going to give you on the next slide a little bit of a better picture of that. But your suppression here is like, you're missing 80% of the jets. So that's a very strong suppression. So the structure of the shower seems to be what's important here. And what might be governing this is essentially a coherence scale. If you have a very fat jet, these two prongs of the jet are disconnected with each other. And so you get more quenching because you have two single scatterers losing their energy independently. Whereas if you have something that's a very narrow pencil-like jet, it's only a single color charge and there's less quenching. And so this actually might be telling you about a coherence scale in the plasma itself. And so this is some very interesting work that's been done on that. This is I think it's great. So I want to tell you about now the path length dependence. This is something that I've done a lot of thinking about here. And here is an actual simulation from a real theorist, not done on my laptop, of the initial energy density in the quark of a single collision. Okay, so the red is the higher energy density, purple is lower, black is vacuum. So you've got something that has a lot of fluctuations. You've got something that has variations associated with it. And I'm going to just throw a jet on here. I just put it here because that's where I drew it. You've got one jet coming out this way, another jet coming out that way. And I'm going to measure the angle of the jet with respect to this psi n. So what the psi n is essentially a measure of the minor axis of the plane here. So this would be the 0 of the phi that I showed you earlier. So that's what's shown here. This is V2 in black. So these are the V2 of the jets. So this is not a pressure gradient. This is really a path length dependent energy loss. So it's different physics because it's at scales that are many, many, many times the temperature of the QGP, right? So the QGP has a temperature of about 400 MeV. These are jets 70 GeV. So there's a lot of space here. So what this is telling you is jets that come out the long side of the QGP lose more energy than the short side. The reason I've switched up the pictures here, though, is because this is obviously not just an American football shape. You can write this in terms of basically a Fourier series, right? There's a triangular component to this. There's a square component to this. Since it's not just, not just an elliptic component, you can just start writing terms. And so that's what this n represents here, is that you can do this not just for V2, but V3 and V4. And so what this tells you as you measure V3 and V4 is essentially gives you an idea of how sensitive you are to small changes in path length. What we see is that we measure V3 to be non-zero in red here, but we measure V4 to be 0. So at least with this measurement, with the sensitivity that we have from this data, we're not sensitive to changes in the path length that are associated with going out the long and short side in some sort of square geometry, but we are in a triangle geometry. So this kind of measure is actually extraordinarily sensitive to the path length dependence of energy loss as it goes through. Okay, so I just want to take a step back here and then talk about a little bit more about how we quantify this and come back to why we're talking about RHIC later on. So I already showed you this nice picture of the jet evolution, and I want to introduce this parameter called Q hat, which is the momentum, the change of momentum squared over the path length. So you can think of this like a momentum diffusion. And so this is a parameter that we use to characterize the overall strength of jet quenching. And so this is not something that you can measure. In the same way we couldn't measure the viscosity when I talked about the liquid nature of the QGP, we can't directly measure Q hat either. And so we use the same kinds of techniques, though, to try to extract this. This is harder because jets are generally a rare probe. It's less advanced than what's been done to extract the viscosity. But you can basically use full simulation, starting from the initial state, going to the measurements. And you can use an Bayesian analysis, again, to constrain Q hat from the data at RHIC and the LHC. So these are two Q hat extractions. They're from two different papers. You can read them here. And what's interesting about this is they're both plotted as a function of temperature, but there's not a lot of temperature dependence here. And so this is particularly interesting. And there's also uncertainty in the temperature dependence. This particular calculation seems to think that Q hat should increase as you go to low temperatures. This one seems to think that something should be a lot flatter. So there's some uncertainty, some theoretical uncertainty into this. It's not really well constrained by the data that's being used to calculate these Q hats. So that's interesting. Why is it interesting? Because the viscosity that I told you about earlier and Q hat, they're both describing the same fluid, right? You should get a consistent explanation. This is a nice paper from actually many years ago now that draws conjectures that a small shear viscosity implies strong jet quenching. So these things should be related. You actually just take a look at that paper. They draw an equation between the viscosity and the quenching in the weak and strong coupling limits. So this is interesting, right? We should be able to get a coherent explanation. And so that might suggest something that we know that the interactions are strong. So that might suggest something about the temperature dependence here. And it tells us that measuring these lower QGP temperatures is probably pretty darn important. So understanding the temperature dependence is really key to constraining this. And I think that that's a general statement that's independent of this particular paper or anything like that. Measuring the temperature dependence of both the viscosity and the jet quenching is key to being able to understand the microscopic nature of what's going on here. So we want to understand lower temperatures. A collider that has a factor of 20 times lower collision energy sounds pretty useful, doesn't it? And so this is a plot that was made for me by Christopher Plumberg, and it basically takes a state-of-the-art hydrodynamic calculation and asks what temperature is the QGP as a function of time at the LHC in blue and at RHIC in red. And so everything we measure is part of some time integral of the QCD or QGP evolution. And clearly you're looking at much smaller temperatures at RHIC over the time range that we're interested in. So RHIC's lower collision energy makes it more sensitive to lower temperatures. And this is really a key thing to being able to understand this. In the absence of being able to put a QGP in a box and change the temperature like you can on your stove, changing colliders is the best way to go. And so that's part of the motivation that me and many of my collaborators have built this project called sPHENIX. So this is a purpose-built jet detector at RHIC. There's a lot of star jet measurements. Many people here are experts in them. sPHENIX is unique in that it was designed much later after STAR to really be a LHC-style jet detector. So it has full hadronic and electromagnetic calorimetry, which means we can measure the energy of all of the particles that come out, those that aren't necessarily charged. And also it has very high rate. So jets are generally a rare process. They're abundantly created, but they're also rare. So this will take data at 15 kilohertz, so 15,000 events a second, really to enable us to sample jets over the full kinematic range that's accessible at RHIC. And this is really a key, along with the LHC measurements, to constrain the understanding of jet physics. So this is a picture of sPHENIX. This is a workshop I helped organize a couple years ago. It is big and complicated, and I will tell you about it at great length if you want. So the run plan, it's completed. So the detector is completed. In 2023, we took commissioning data with the gold beam. I'm going to show you some initial results from that. The run was truncated by a cryo incident at RHIC that prevented further running in 2023, which was unfortunate. Those seem to be fixed. And so starting in April of this year, we're going to take the proton-proton baseline measurements so that we can take a lot of ratios. And so this is our essential baseline measurement. Some gold running also to finish up some of the commissioning steps that we weren't able to in 2023. And in 2025, high luminosity gold running. So this is where we'll take the data set that will allow us to really make these kinds of measurements that I've been showing you at the LHC, also at RHIC. So this is the run plan as it exists. There's other exciting opportunities that are not allowed in the existing schedule because of the need to transform RHIC into the EIC. I think it's very clear to say that this is the plan. That doesn't mean that these things are not interesting at all. I'm very excited about them, and I've told many of you about them all day long. So the details, you can find some of the details here. So both the sPHENIX and the LHC jet measurements are really key to constraining this physics of jet quenching. So I will take 2 minutes to tell you in 1 minute. My group built the EM-CAL, which is a tungsten powder scintillating fiber detector. So if you're a photon headed into sPHENIX, this is the last thing you see. Scintillating fibers here in this grid, tungsten powder there. We built about 5,000 blocks and lined them up this way into sectors. There's a couple of our students and our postdoc installing them into sPHENIX. And here behind this yellow tape, you can see it when sPHENIX was mostly installed. Now it's all the way installed and you can't see it anymore. But that was an experience. It was a lot of fun. And what's great is to be able to see sPHENIX in action. So these are just 2 of the plots. There's a lot more. So this is the pi0 mass peak. So the pi0 decaying into 2 photons. It's not in physics units here. This is in ADCs, but that's fine. You can see the mass peak here and then the combinatoric background. This is a plot that was just shown last week for the first time. This is about the energy underneath a jet cone as a function of centrality. So you can see that in these very head-on collisions here in red, there's a lot of energy underneath the jet cone. These very peripheral collisions that are shown in black, there's less energy. So this again tells us that we have sensitivity to the QGP geometry. And so there's a huge effort underway to analyze the existing data. It's not as full of data set as we hoped for, but there's still a huge amount of things that are being done with it, publications on the way. And in parallel, of course, we're preparing for the upcoming data taking to begin in a couple of months now. So actually, I think this is a great time to be studying the QGP because there's a wealth of data, and I've only shown you the smallest fraction of it. So this is an event display from sPHENIX. Here's one from Atlas. The entire LHC program in Run 3 promises so much more data. This is actually fantastic. I haven't really touched on our theory friends at all, but there's new techniques. Ian can tell you all about those. There's Bayesian analyses to help constrain this stuff. There's other theoretical progress as well. And this will really allow us to really qualitatively improve our understanding of nature's hottest fluid. There's a missing apostrophe. So actually, I think this is part of a golden age of QCD, right? I've told you about what we can do experimentally at RHIC and the LHC, in part. But there's a lot more. There's the electron ion collider that's coming in about a decade. There's these Bayesian analyses I've told you a little bit about. There's a lot of improvements in lattice QCD. There's a lot of also connections with the high density limit in neutron star observations coming from LIGO and the theory associated with that as well. So, I started off with QCD being experimentally motivated, but there's a huge amount of work on the theory side and connections between various aspects of QCD that really allow us to make qualitative improvements, and I'm very excited to be working on it. So thanks a lot.
Okay. Thank you, Anne, for the very nice talk. Do we have any questions?
I think I missed something very basic when you
Okay.
introduced, I guess it was V2, the two colliding pancakes, and you measured this angle phi from the symmetry axis of the collision. You assumed the offset of the two was like horizontal, but
Yeah.
we don't have, how do you, we don't know that. So how do you?
That's a great question. It's a real stinker of a question too. I will tell you about it, and I purposely left it out because there's two ways you can do it. So the first thing you can do is you can basically assume that everything is in plane, and you can measure the debris that goes in the semi-forward direction. The real way to know that V2 is positive and not negative, though, is to measure the spectators, because they tell you really these things that don't interact, the lightly shaded ones. If you can measure that, you can know for certain that V2 is positive. And so we know that at RHIC and the LHC, we know that V2 is positive. And so we generally don't measure the spectators. We usually do it via other techniques. One thing that you can do is two particle correlations. So that will give you V2 squared. So you can look at all the pairs of particles and you can extract V2 squared from that. And that's a technique that's very common.
I guess I meant, how do I know which direction is phi equals 0?
Because you measure the spectators that come off. And so you know where they are, if they're like this or that or whatever. Yeah, that's a great question.
Any other questions? Maybe I can ask a question. So you talked about in the XJ how the reason why you see less suppression for the asymmetric is because of maybe a surface bias effect. But have you also thought about maybe how the different structures of the different composition of the different dijet pairs and how that might play a role?
I think that's a really great thing to look at. And I don't have an answer, but that's a question that I think is really great. And I would love to, and maybe this is, people here who are experts in multi-dimensional unfolding, to be able to correlate something like this with the jet substructure to bring these together. I mean, I really showed these as separate bullet points, but it's one system. And so correlating them with each other sounds very difficult experimentally, but very interesting physics-wise. So I think that's a great question.
Thanks. Any other questions? Do we have any on Zoom? Okay. If not, then let's thank Anne again.
Thank you.